Hello again everyone, welcome back to ptet.chemistry channel. So this is a continuation of this qualitative analysis kind of experimental video, where in this tutorial video I specifically want to investigate the identification, not investigate, I want to show you the identification of the cations. The various cations, they are not just only assessed as part of the O-level or the IGCSE or the GCSE qualitative analysis curriculum, but also what is continuation. They are being continued when the students go to A-levels as part of the paper 3 practical assessment as well. Okay, so in my other tutorial series I've talked about specifically on water crystallization, and I've talked about the identification of ammonium ions, and also when you have the presence of ammonium as a double salt or ammonium nitrate, for example, a very tricky one. There was in that other tutorial video. And then there was also another tutorial video on qualitative analysis where I talked specifically on this idea of double salt, or a mixture of two compounds in one particular solid mixture, where you are not only testing for one cation, you could be testing for 2 or 3 different cations. Okay, and this tutorial video is a very standard. Oops, let me just get it started. So I just started this screen recording where I'll probably be going on and off. I'll be looking on my screen where I'll screen shade as a picture-in-picture if I get to edit this video given time ready. So we'll have an array of test tubes. I have a bunch of chemicals here. So in this video I will also use some materials that I've used for the other qualitative analysis tutorial video. We have talked about the NH4 plus, Fe2 plus, you need 2 of that, and the SO4 2 minus, you need 2 of that. That was the source of iron 2. I'll show you in the other tutorial videos. I'll probably use the same fit here so that I'm not wasting chemicals at all. As you know, chemicals are expensive, and that's why you need to cherish every single opportunity you get in the lab. So this is a +1 and a +3. So this is the -2, I need 2 of it. This is iron 3. So my focus in this tutorial video is not to think about the ammonium ions, which I already went about identifying in my other tutorial video. Of course, my focus here is also not on the anions, which I also identified in the other video. My focus here is on the cations as part of the bigger study, or the overall framework of this tutorial video is really to talk about the cations present. Okay, the other cations that we'll be talking about is also this thing on chromium trichloride. Okay, so this is a hexahydrate. I talked about water crystallization, and this was one of the compound featured. So here we will be using chromium trichloride, hexahydrate. It doesn't matter whether it's hydrated or not, because when they provide you with the solution, if you are provided with the solution in exam, then the solution does not matter whether it is hydrated or not, because it will have been dissolved in distilled water anyway. So for most of my stuff today, I'm just really scooping out a bit of solid from the bottle itself, so I'm not being given it as a solution like what you would have in a real exam. Okay, so we would use distilled water or deionized water, because they contain no dissolved ions. They contain no dissolved ions that can interfere with our qualitative analysis. The objective for qualitative analysis is to identify what are the cations and anions present. If you use tap water that contain dissolved ions, they will interfere with your qualitative analysis results. So chromium chloride .6H2O. In the solution form which you will be provided, there is the chromium 3 plus aqueous. This is the identification of chromium 3. Okay, so the oxidation state of chromium, there is chromium 3. And what else? There's some copper 2 as well. So this is copper 2 sulfate anhydrous. It's a bit whitish because you're removing the water crystallization. But I also talk about, where is my copper These are the copper 2 sulfate hydrated, and these were the nice and crystalline form, which we can then dissolve in water and they'll give us our blue color solution. Okay, so you deal with Fe2+, Fe3+, Cr3+, as well as Cu2+ as your colored compounds as a result of these transition metal cations. Alright, in O level, in A level, there is also 2 additional cations that you will have learned. One of which is this cobalt. This is cobalt chloride. It's actually part of the A2, which is the second year of A-level chemistry syllabus. This is a pink. This is a pink color solid, and when it's hydrated, it is pink. And when you have this solution and you coat it onto the filter paper, this is the test for. Oops, sorry. When you remove the water crystallization, then it becomes blue. Then the anhydrous cobalt chloride is what you coat the filter paper, and it will be blue in color. And you test for the presence of water, which will give you this compound, which is blue, which is pink. So we use anhydrous cobalt chloride to test for water or water vapor, and it will turn from blue to pink, giving us back the hydrated form again. You don't really have cobalt 2 analysis in paper 3 practical, but cobalt 2 is an important case study for the A2 transition metal chemistry, A2 being the second year of A-levels. I'll cover that in a separate tutorial video as a case study into cobalt chemistry. But there is one thing which is looking for manganese. This is manganese 2 chloride. Not too sure if it's clear or not. Okay, it's autofocus now. This is also a hydrated salt. Manganese 2 chloride. As you can see, it's a pink color solid. It will give you a pink color solution. And I don't know what's wrong with the bottom of it. It looks a bit disgusting down there. Anyway, so it's a pink color solid. Mn2+ being an ion of the transition metal. It forms colored compounds, and most likely, depending on concentration, it will also give you colored solution. I said depending on concentration because if your concentration is very dilute, it might look almost like colorless, such as this manganese 2+, which I'll show you in a little bit. Okay, so we will have manganese chloride 4H2O. Again, once in solution, it really does not matter if it's hydrated or not, because what you will have is manganese 2+ aqueous, and that is the manganese 2. I showed you earlier the cobalt 2, but we don't really cover that as part of the A-level paper 3, although cobalt 2 or cobalt chemistry in general is a major case study on its own as part of A2 transition metal chemistry. Okay, I also have copper 2 sulfate. Again, the water crystallization shouldn't matter because I'm going to dissolve them in water, and they'll give me copper 2+ aqueous. So that is your copper 2. Alright, so I want to talk about these transition metal cations, iron 2 and iron 3, which I already shown you the observation in the other videos. So I'm just going to use the materials from the other video and show you the result for iron 2 and iron 3. Okay? Or I might actually show you here actually. So iron 2, iron 3+. So we're going to have a table really. Okay? So we'll have aqueous and then OH, and we have aqueous NH3. So let's think about. So this is just a very, very simple table. Not too sure how straight it is. Okay. So let's get started with our test tubes. Actually, I will skip the iron 2 and iron 3 because there will be materials from the other tutorial video, which I'll show as a picture in picture as I'm writing the result for this. You will see the color change that I will have that I'm showing on the screen right now as part of the picture in picture resources that are being recycled from the other video. Okay, sorry, I was just thinking about what to say. So iron 2+ in the presence of NaOH. Or maybe I'll show you actually. Okay, maybe I'll just show you. Doesn't take a lot. So this is iron 2. This is actually ammonium iron 2 sulfate. So what they could give you an exam instead of this, they could give you iron 2 chloride or iron 2 sulfate as a solution. So I'm not too concerned about the ammonium ion here. So it looks a bit colored actually, but it's not very clear. So this is the iron 2 plus in solution. Iron 2 plus in solution. Let me go and grab a white background. A bit colored, but not really that intensely colored. This is iron 2 plus in solution. So remember, this is iron 2 plus aqueous. It is not a solid. Aqueous means it's a solution, and this is without hydroxide in it. Okay, so this is actually supposed to be a little bit pale green. Okay, it's a pale green solution. It's not very clear on the screen, but if I just have pure, I think my other redox titration video, I have a lot clearer iron 2 salt. This because there's a lot of ammonium salt dissolved in here as well. Anyway, so what I'm going to do is I'm going to separate it into two portions. One of which I'll test with ammonia, and the other one I'll test with sodium hydroxide. Okay. So I'm not that interested to test for the ammonium cation because I know it contains ammonium cation, and I could just, after I add extra sodium hydroxide, I could just warm it and I get pungent gas that turn red lemon pepper blue. They will tell me ammonia is present. They will tell me that this thing also contains ammonium ion, and that was what I did in the other tutorial video when I used this ammonium ion 2 sulfate versus the ammonium ion 3 sulfate to show the presence of ammonium ion in both. Okay. I'm not going to do the ammonium test here. I'm interested in the test with sodium hydroxide, NaOH, as well as ammonia, aqueous ammonia, NH3 dissolved in water. Okay, so I want to do the NH3 first. This is iron 2 plus in NH3. So you get this precipitate, and this is a precipitate because you cannot see through. You cannot see through at all. Okay, this color looks about the same color as my shirt. Actually, it's by coincidence. I think I mentioned in the other video. This is a green precipitate. This is a dirty green precipitate. Dirty because it's kind of dark in color. It's very characteristic of iron 2. However, if you know chromium 3, which I'll show you in a little bit. So this was with aqueous ammonia. We get a dirty green precipitate. PPT refers to precipitate is formed or is observed. Then what happened when I add in excess? This is ammonia. I'm just going to add in excess and see what happened. So this is already in excess because just now it was around there. I added way more. You could add way more again. And because you're adding ammonia, obviously you will smell ammonia. Okay, so that you're not testing for ammonium ion here. You never test for ammonium ion by adding ammonia because it will definitely smell of ammonia. Okay, so it is not see-through. So the precipitate is insoluble. Okay, so the dirty green precipitate is formed. The PPT, the precipitate, is insoluble. Insoluble means does not dissolve, and this is in excess. Excess what? Excess NH3 aqueous. Alright. So there was the test for iron 2. This was my other solution of iron 2. Okay. So that was clear before I added in any hydroxide. So here I'm going to add sodium hydroxide, and let's see what happened. Iron 2 plus with sodium hydroxide give me the same color kind of precipitate. This is a dark green or dirty green. Okay, it's not really dark green. Okay, it's dirty green. It is a precipitate. You can't see through it. Okay, so with aqueous sodium hydroxide you get the same thing. Dirty green PPT is formed. Then how about when I add excess sodium hydroxide? So this is around 1 cm cube. So if you add excess, it's gonna be way more. So adding aqueous sodium hydroxide in excess to this thing, it looks like it is dissolving. It looks like it is dissolving, but you cannot see through it. If it is a clear solution, you can see through it. If it is a solution, you can see through it. You cannot see through this. It looks like it's dissolving, but it is not. Okay, it is not a solution because you cannot see through it. So what we say is the precipitate is insoluble in excess NaOH aqueous. Alright, so that was a test with iron 2. Okay, instead of going straight to iron 3, I just want to highlight the chromium 3 test first because that is a really important distinction, because chromium 3 plus aqueous also give you green precipitate. So this is the chromium 3 chloride. There are other chromium 3 compounds, of course, and they will give you as a solid or as a solution. So what I'm doing is I'm just taking a little bit, not a lot, just a very small amount. Because even in exam, okay, you see, I don't know if you can see. Okay, so there's the metal spatula and there's a bit greeny, kind of green solid. Okay, so the chromium 3 chloride is a green solid, and it gives me this very nice green color solution. You see, very nice green color solution, kind of light green solution. So it's very easy to tell, really. I mean, just by looking at the color solution. You remember the iron 2 was not very intense color, right? So even after I add water, the green color as a result of chromium 3 plus is still pretty green. Even after I add a lot of water, it's still pretty green. Remember the iron 2 plus as an aqueous solution, it was never going to be this green, okay? Even though I use a lot of that solid just now, it was never going to be as green as this, even though I use only a very little amount of the green thing, okay? So these are different shades of green. I'm going to separate them into different portions, okay? Ideally, I should be testing for the anion. The anion is chloride, so here I'm testing for the anion as well. I know the anion is chloride. I'm not going to write on the table, but I just want to show you that it was chromium. It's chromium 3 chloride, so it's an ionic compound. This is chromium 3 plus in solution. I'm adding silver nitrate. Silver nitrate solution is clear, by the way. It is a clear solution. And what do you see? You definitely get a precipitate. The question now is, because of the green color, because of the light green color of the chromium 3, you might mistakenly think that this is a green precipitate. This is very clearly not a green precipitate. It's actually a white precipitate, but it's very difficult. It's very difficult to identify the anions with silver nitrate because your cations give you the colored solution. So this can be asked as a question like, why is it difficult? Why is it you are not certain? Why you cannot confirm 100% for sure that it's chloride? Because silver chloride is white precipitate, silver bromide is cream precipitate, silver iodide is yellow precipitate. The color itself might be affected by the color of the transition metal ion, which is still present. So this one it looks white, but if my solution was quite concentrated with green, this one might look a little bit more green, but obviously it's not the chromium 3 plus that precipitate out with the silver nitrate. It's actually excuse me, it's actually the silver plus from the silver nitrate that reacts with the chloride to give you silver chloride solid. As I show you on the screen here, this is a precipitation reaction, but that is not what I'm interested here. I'm interested in the identification of the cations. So the first thing I'll do here is to add ammonia. Okay, so ammonia. So this is the chromium 3+. I add ammonia, and you notice that there is a slight cloudiness because there's a precipitate being formed. Okay, it looks a bit like whitish, but then because we are doing something to the cation, it cannot be whitish because it's the chromium 3+ that actually forms the precipitate. You started with a colored solution which indicate to you that you have a transition metal cation most likely, okay, or transition metal in there which will form cations. So there is a colored precipitate. It's not very concentrated because remember I only scoop out a small amount, very small amount, whereas in the real exam, Cambridge will ask the centers, will ask the supervising teachers to prepare the solution to a particular concentration. They will be easier to notice or to observe the changes. All I did just now was just a very tiny spoonful. It's not to an exact concentration, so it's not going to be super exact, but how you can see it's colored, and that is a result of chromium 3 hydroxide being formed. But I did not add sodium hydroxide, I added ammonia. Then where did the hydroxide come from? Because ammonia is basic, ammonia is alkaline. You should have learned this in your theory. NH3 is a weak base. A weak base because it reversibly okay, ionizes, or it partially ionizes. Reversibly, we can say partially, and then you can use the word ionizes, or you can use the word dissociates into OH minus because it's a base. So it dissociates OH minus in solution. The solution referred to in water. Can you write an equation to show this? Of course, NH3 plus H2O reversibly give you NH4 plus, which is ammonium ion, and OH minus reversibly partially ionizes. The equilibrium favor the left hand side because it only partially ionizes into OH minus ions. It's a weak base. So when you get this precipitate, it's the same thing as the chromium 3 hydroxide when you add sodium hydroxide to it. This was adding ammonia to chromium 3+ aqueous. So I get a green precipitate. It's definitely a precipitate, by the way. So the right hand side was with ammonia, so you get a green PPT is formed. The question is it soluble in excess ammonia, or is it not soluble in excess ammonia? So I'll add ammonia. Sorry, where's the level? I'll add ammonia to this thing. Is the precipitate soluble or insoluble? Can you see through? You still cannot see my eye, right? Because it's not completely clear. I've added a large amount of excess NH3. My stuff was not very concentrated to begin with, and I already added excess ammonia. It is still insoluble. So a green PPT is formed with chromium 3+. When I added aqueous ammonia, the precipitate is insoluble in excess NH3, NH3 aqueous. So what will happen then if I add it to the other portion? This is the chromium 3+ aqueous. I'm going to add sodium hydroxide now. Sodium hydroxide. I'm slowly running out of solution actually. I should use the dropper, but I roughly know this is the solution I have. I should add equal amount around my finger length there. Oh no, it is not very clear at all. Okay, it's not very clear at all, I think because my solution is very dilute, but I don't know if you can see it or not. Oops, sorry. Okay, so it looks like there is a little bit of things in there. Okay, there is like a little bit of solid in there. It's not very clear, but it looks pretty clear, but it's not very clear. I know what I should do. What I can do is I can add a little bit more of the chromium 3+ to this thing. Okay, this is what I meant by This is what I meant by like the actual exam. They will give you a more concentrated solution according to Cambridge standard. Where's my chromium 3 chloride? Here it is. So I don't reuse my spatula, I use the other tip which is clean. So I have a larger spoonful here. By the way, chromium 3 plus I think is okay because it's in the syllabus. Chromium 6 plus is carcinogenic. So here the solution is a lot more concentrated, right? A lot more concentrated. Let me add a little bit of sodium hydroxide to this. This is a see-through solution. I hope you can see that. It's a clear solution. Okay, clear solution, not a precipitate. When I add sodium hydroxide, so now it's very clear it's there because I have a lot more chromium 3 plus in there. So it is not, actually it's really hard to see. Okay, it's really hard to see because it looks like it is still dissolving actually, but I could see solid at the bottom. I don't know if it makes sense to you. I could see the solid at the bottom. Okay, it's supposed to precipitate out with a little bit of sodium hydroxide. Okay, but when I add a lot more sodium hydroxide, all the precipitate is supposed to dissolve. Okay, how then in the world are you supposed to distinguish between the iron 2 hydroxide, which was also green precipitate? Was that the green precipitate that you get with iron 2 very obvious, it precipitated out, whereas the green precipitate that you first obtain with chromium 3 plus, it's very difficult to see, but then when you add too much sodium hydroxide, they will dissolve straight away. Okay, they will dissolve in excess aqueous sodium hydroxide. I'm afraid it's not very easy to see, but when I added a very small amount of sodium hydroxide, you could see at the beginning just now, if you rewind the video, that you obtain a white precipitate just now. Sorry, a green precipitate. But what is different, you see? What is different is that iron 2 plus has the same result with both NaOH and NH3. The precipitate remain insoluble in excess NH3 and also excess NaOH. But what is different between Cr3 plus in terms of adding NaOH and also adding aqueous NH3 was that in NH3 the precipitate was insoluble in excess NH3, but the chromium 3 hydroxide precipitate is soluble in excess NaOH aqueous. And this is how you can distinguish between the dirty green precipitate for the iron 2 plus. This was the chromium 3 plus in excess NaOH. This was the iron 2 plus in excess NaOH. They remain insoluble. Okay, the solid settles at the bottom. This one is chromium 3 plus. The precipitate that you formed initially was chromium 3 hydroxide that dissolved in excess hydroxide. The iron 2 hydroxide is insoluble in excess hydroxide. Okay, so in terms of equations, you can obviously write precipitation reaction. So Cr3 plus OH minus, you need 3 of them to give you CrOH3. This was the green precipitate you get at first. This is the precipitation reaction. And when you write precipitation reaction, it's basically the same type of reaction as this precipitation of silver chloride, which I'll wrap up now because we are not testing for the chloride here. I just showed you earlier. Okay. In terms of what happened here, the dirty green precipitate is actually represented by Fe2 plus aqueous plus 2OH minus aqueous, giving you FeOH twice solid. Fe2 plus aqueous is meant to be a little bit pale green depending on your concentration, and then this is aqueous and aqueous, both are solution. They precipitate out to give you this dirty green PPT, which remain insoluble in both NH3 as well as NaOH. Okay, so not that there are answers for the equations, I just thought it would be nice, but now I'm just going to wrap it out because it might be confusing since we are doing observations and we are not doing equations or we are not doing solution just yet. Okay, iron 3 plus, iron 3 plus. So now I have this thing, ammonium iron 3 sulfate. Doesn't matter what the anion is. I'm more interested in the cations. So this is also a double salt, but I already tested for the ammonium ions in my other video. So what I'll do here really is I'll just dissolve this in water. Okay, it looks like a white solid, but when I dissolve it in water, it's kind of give me a brown solution, an orangey brown solution. Okay, this is very clearly a colored compound because it's a pure mixture. By the way, it's a mixture of two different salts. I want to try and dissolve it as much as I can before I test for it. So I'll put it into two different portions. I just want the solution. I don't want the solid. You see, there are some solids settling at the bottom. So if you just let it settle for a bit, which you know in exams they will just give you a solution like this. Okay. So there's ammonium iron 3. Ammonium iron 3 sulfate, does not matter. It has iron 3, it's a solution. I'm going to add ammonia. I add ammonia a little bit, so around this level. It's not a see-through solution, okay? You see, it's kind of cloudy, it's kind of blurry because it is a precipitate. It's not a see-through solution. Okay, it looks like it's not very concentrated because I've used a mixture, a double salt, right? So double salt is a mixture, whereas if you use a pure iron 3 salt like iron 3 chloride or iron 3 sulfate, which is in stock, but I don't want to go back in store and actually do it. But if you see closely, it looks like, I don't know if you can see it, it looks like there are some precipitates suspended inside the solution. So this is an orange, reddish brown actually, they call it reddish brown. This is an ammonia, so you get a reddish brown PPT. This looks more orangey. In reality, when you have pure iron 3, the precipitate is supposed to be more reddish brown. Okay, but this is straight from your qualitative analysis notes, the table that you provided, and I should try and add excess ammonia. It looks like it dissolved. It looks like it dissolved, but look very carefully. Not too sure if it is clear or not. There's like suspension again. Okay, so it looks like most of it dissolved, right? But if you look carefully, there's a suspension that doesn't want to go away. Okay, it's a suspension. The solid, the precipitate is very fine. It is still suspended within the solution. Okay, so it looks clear, but you see the solid being suspended, and now it's clear. Okay, so the solid itself, the precipitate, is actually insoluble. Okay, because you still have it lingering around in the end. So this is what you call insoluble. Whereas some students at the beginning of their qualitative analysis, they would have thought that this is soluble, when you could still see the precipitate. It doesn't go away in excess NH3 even if I shake it. Now to the other portion of the solution, I will add some sodium hydroxide. So I have this much solution. By right, usually we start with 1 cm³ and then we add 1 cm³, but this is probably less than 1 cm³, so I'll probably add around this level only. Okay, and I get a similar kind of results. You get that cloudiness, you get that precipitate forming. Is my white background. Okay, not too sure how clear it is, but it is a precipitate. Can you see it does kind of block the writing at the back? So this is also a reddish brown PPT. Is formed, always observe. And then what happened when I add excess sodium hydroxide to this? Excess sodium hydroxide. If I use up my sodium hydroxide, I need to go and get some more. Okay, it's the same issue again. So you get that suspension, all right? You get that suspension. The solid doesn't go away, the precipitate doesn't go away. When I started here, I added this much, and then this much is in excess. You could add more and more sodium hydroxide. Oh, actually I have another bottle of sodium hydroxide. Na plus, OH minus. I could just add more. And they do not go away, okay? You see like there's a reddish brown suspension. So this is telling you that, you know, the precipitate is insoluble in excess NaOH. Okay, so now I'll go through the next cation, which is actually in the O-level or the IGCSE syllabus, which is the copper 2+ cations. So the copper 2+ that I'm using is the copper 2 sulfate hydrated. So it's usually given as a blue color solution in your exam. So when you see a blue color solution, most likely it has copper 2+, but do not take it for granted, okay? So always test for it and confirm the identity, okay? First of all, colored solid, okay, that contains metal, which means metal cations. Most likely is a transition metal cations, it's a transition metal compounds, but then you need to test for it. So I'm just going to dissolve it in water. So this thing is actually quite hard to dissolve in water. They don't like to dissolve in water at all. Okay, some of them already started to dissolve in water. Doesn't matter. Very crystalline solid, very beautiful crystals. My solution has already started to go a bit blue. I don't want the solid actually. So what I do is I just get the solution like this, pale blue solution. And then, so it started with copper 2+. Copper 2+ is a pale blue solution like this. What I'll do is I'll add some ammonia to it first. Okay, this is ammonia. Alright, so add a little bit of ammonia and you get a precipitate, no longer solution. You get a pale blue precipitate in a little bit of ammonia. So the pale blue solution, well, sorry, you don't get a solution anymore, you get a PPT, a precipitate, because this is a solid, it's not see-through. Then I'm going to add excess ammonia. Ooh, I hope you saw the color changes. And let me shake and shake and shake and shake. Don't know if it's clear to you, this is meant to be a blue solution. All the solid has disappeared. Let me add a bit more ammonia. It's not very clear, but it is clear that, you know, it's no longer the pale blue precipitate. It is now a dark blue solution. This is what they call a dark blue, or you can call this deep blue, DEEP, deep blue or dark blue solution. So the precipitate dissolves in excess ammonia. Okay, the precipitate is soluble, or they can say, or you can say, dissolve in excess NH3 aqueous. But it's an observation, it's qualitative analysis. So make sure that, you know, you give all the observation you can to give dark blue. If you want, you can use deep blue. It's a solution, it's not a precipitate. It's a solution. I hope you can see. Okay, it's not a precipitate anymore, it's a solution. The previous pale blue precipitate is gone. Okay, I'll talk more about this in another separate tutorial videos where I'll go through the A-level concept involving the specific case study of copper 2. Okay, but I'll just stop there with the qualitative analysis. and I'll have to test the other portion. Sorry, where is it? Here is the pale blue solution, and then I'll add some sodium hydroxide. Sodium hydroxide and then OH. Make sure you know the formula. You can see that, this is a precipitate. It's not a solution at all. This is a precipitate. You also get a pale blue precipitate. This form. As usual, we need to add excess sodium hydroxide. So this is sodium hydroxide. I have this much, so I'm going to add excess by pouring the sodium hydroxide in. Yes, the color has gone deeper. The color has gone deeper, but it is not a solution. Okay, I can add more sodium hydroxide. So the color has deepened again, but let it settle. Oops. This was the deep blue solution, the dark blue solution in excess ammonia. This is in excess NaOH. You see the difference? Solution on your left, okay, this is in excess NaOH on the right, this is in excess ammonia on the left. Okay, this is a solution, this is a deep blue or dark blue solution. This is the precipitate, because you see it's a suspension. Okay, it's a suspension here on the right hand side, on your right hand side. Okay, so in excess NaOH, the precipitate remains insoluble. You see the suspension, but in excess NH3, the copper 2 hydroxide, which is the precipitate by the way, when you have copper 2 plus aqueous plus 2 OH minus aqueous, remember that ammonia is a weak base. We talked about it earlier. Ammonia is a weak base, give you the hydroxide. When we added ammonia in a little amount, it provides you the hydroxide. It's the same reaction as the hydroxide reacting with copper 2 plus. It gives you something called copper 2 hydroxide. Copper 2 hydroxide is the pale blue PPT. This is the pale blue solution. Okay, but then this pale blue precipitate was in NaOH, and the precipitate is insoluble. The precipitate is insoluble in excess NaOH aqueous. These are the kind of results that tells you really the copper 2 plus is present. This is test number 1. This is test number 2, just to confirm it further. Okay, so in a separate tutorial video, I will specifically talk about and discuss about the underlying reactions. It's actually related to an A2 transition metal concept, so I don't want to confuse you by going through this qualitative analysis and the explanation right now, because one is more experimental observation, the other one is more theoretical, but it's all based on the experimental results. So I'll discuss it in another separate tutorial video, depending on my time, really, sometime in the near future. Okay, so the last cation that I want to talk about is actually something that is in the air level, paper 3. Oops, what am I doing? The air level paper 3 is the manganese 2 plus ion. So this is called manganese. Oh, what am I doing? Manganese 2, or they call it Mn2 plus aqueous. So all of you should be familiar with something called potassium manganate 7, meaning VII. Potassium permanganate 7 is the same as potassium manganate 7. This spelling is a bit weird. It should be potassium permanganate 7, and this has the formula of KMnO4. Not sure if it's clear. KMnO4 there on top with the molecular mass, or the Mr. Okay, so it's this purple color solution, but it looks really dark looking, kind of blackish. I don't want to let it stain my shirt or whatever, because it is very oxidizing, and the color, the intense color of the purple color, you will have used it for titration, or you have seen it before, definitely. Okay, You can watch my other tutorial video on the redox titration between acidified KMnO4 with Fe2+, and you can see how intense that purple color is. And that was the original solid that you make up the stock solution that you fill in the burette or sometimes in the pipette. Okay. What I want to test, however, is this thing called, where's my manganese? Manganese 2 chloride. I swear I had it earlier. This thing, manganese 2 chloride for hydrate. So it looks like a pink color solid. When MnO4- act as an oxidizing agent, you're supposed to get Mn2+. That's the usual redox equation that you write, and that pink color Mn2+ is supposed to be this in aqueous solution. But when we are dealing with solution chemistry, the concentration might be too low that sometimes it appears like colorless. Okay, it appears like colorless. So we're just looking at when the purple color disappears or when the first permanent hint of purple remains, depending on whether you have the purple color solution coming down from the burette or if you have the purple color solution pipette out into the conical flask. So what I'll do is I want to test for manganese 2 plus. Great test tube. So this is not in the O-level syllabus actually, but you never know what will come out in the future, right? I know it is in the A-level paper 3. I think no one has used this solid for a long time. Very, 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 very hard, yeah. But I don't need a lot of it. I just need a small amount in order to show you what it is. It's a manganese. So remember, it was a hydrated compound, so it's got water crystallization. My spatula was dry just now. My spatula was dry, and you see it looks a bit wet now, and that's because the water crystallization, I think, has started to come off, and that's why you get a bit of liquid water, and it looks a bit wet. Doesn't matter. Okay, so I'm just going to dissolve it in distilled water anyway. So when you have a hydrated compound, when you are provided the solution, it does not matter anymore because the water crystallization, they will have just become part of the distilled water or the deionized water that make up the solution. You saw the solid just now was kind of pink, right? But the solution looks really colorless. Even against the white background, it looks colorless. It was manganese chloride. So ideally speaking, I can test for chloride as well. Maybe I have enough, so I'll save one for NaOH. I do have another test tubes. So, oh no, this is dirty. Okay, I don't want to wash up too much test tube afterwards. This is a bit dirty. It's got a bit of browning on the upper part there. It's inside, but just be aware that this thing is already there when I did this reaction. So anyway, this solution is clear. This is the one with a little bit of browning there in the test tube. It's not a result of this reaction. It's just there in the test tubes already. Okay, so the solution is clear. This one contains manganese 2+, and it contains Cl- because I started with where's my here is manganese 2 chloride. Okay, to test for chloride, you use something called silver nitrate. You see, even the level come off a little bit. Silver nitrate stains your hand, yeah, because the silver one get reduced to silver very easily. It tests for halide, tests for chloride, tests for bromide, tests for iodide. When you add silver nitrate to something that contains chloride, bromide, or iodide, you get a precipitate straight away. The color of chloride, silver chloride and silver bromide is very difficult to differentiate. Okay, these are something that is only differentiated in A levels. That's why you need to add excess ammonia to this. But my ammonia is running low, so I don't want to add excess ammonia to this. But if you are an A-level student watching this tutorial video, you know that to determine whether it's silver chloride or silver bromide, you need to really add excess ammonia, aqueous ammonia to this. If it dissolves, then it's a chloride that was present. If it does not dissolve in dilute, meaning aqueous ammonia, then it must be bromide. white and cream, white precipitate and cream precipitate, very difficult to differentiate, to distinguish, to tell apart silver chloride and silver bromide. However, it's much easier to distinguish a yellow precipitate. If you have a silver iodide, Ag plus I minus, AgI, the yellow precipitate is very easily distinguished. Okay. Anyway, I'm not going to test for the chloride here. I'm more interested in the test for the cations. So I have my two solutions, which, to be honest, they look really colorless, yeah, because of the low concentration, even though it looks like a pink solid just now. I said my ammonia is running low. It is running low, so I'll add a little bit, and then I'll add in excess. Okay, just add a little bit, and you see a white precipitate. Okay, so this is a white precipitate. If I'm not mistaken, in the qualitative analysis note, they give you Mn2+. It was a white precipitate, right? It was a white precipitate. What do you notice now? The white precipitate has gone off white. It has gone a bit brownish. Okay, so it's gone a bit brownish. It started from the white precipitate. You can rewind the video, and now it's gone a bit browny. Okay, this is called off-white. Some people call it coffee. It's gone from a white precipitate to like coffee color there. So I should have written it down first, but anyway, I don't want my ammonia to escape as a gas anymore, so I'll just add the ammonia in excess. That was actually excess ammonia already, because I started with this much, I added this much, and then I added even more ammonia. When I added even more ammonia, you could add up until here, this white precipitate does not dissolve anymore. I beg your pardon, it's not a white precipitate, it's more like a off-white, off-white precipitate. It's more like, I don't know, they call it cream, they call it coffee color, but in the qualitative analysis table provided in A levels, this was in ammonia, so you get a white, or you can say off-white ppt is observed, or is formed, or is obtained. The precipitate is insoluble in excess NH3 aqueous. It remains, it's gone off-white again. Okay, remains off-white. Okay, so some people will call this coffee color. It looks a bit like, it's a bit creamy actually, so it looks a bit creamy instead of white. Okay. Anyway, I'll just finish off the last test on manganese 2+, which is to add sodium hydroxide. So I'll start by adding a little bit of sodium hydroxide first. So again, I think it's gone off-white very quickly. Yeah, okay. You can tell apart white precipitate and off-white precipitate. Hope you can tell that it's not exactly white. Okay, and it's not pink as well. This is kind of creamy, like coffee color. Not too sure how the color saturation or the balance will be like in these videos when they turn out. So this was the sodium hydroxide. So again, you get a white. Well, actually, off-white would have been better because it was definitely not white. It's definitely not white. In sodium hydroxide, it's definitely not white. So I call it off-white. PPT is obtained. So you can't really call it white PPT, yeah? So I should knock off the white PPT with the ammonia just now, yeah? Now, what I'm going to do is I will add excess sodium hydroxide. I hope it's clear to you that the solution is not clear, even though I added excess sodium hydroxide. It's still a bit murky. Actually, there's the precipitate lingering around as a suspension. Oops, sorry. Again, use something a white background, like a white tile or something if you can't see it properly. Okay, this is manganese 2+ in the presence of hydroxide, and then I added excess. The precipitate remains insoluble. So the off-white precipitate remains insoluble in excess. NaOH aqueous. Okay. So that's it in this tutorial video. I have not done qualitative analysis of every single cations in the qualitative analysis table. Instead, what I've done is really just to do a couple of these transition metal ions, including Fe2+, Fe3+, and Cr3+. Remember the green here and the green here. The green color precipitate, the iron 2 hydroxide and the chromium 3 hydroxide, can be differentiated by adding excess NaOH, where this iron 2 hydroxide remain insoluble, but this chromium 3 hydroxide is soluble in excess NaOH. Copper 2+ aqueous, the differentiated results in the presence of excess NaOH as well as in excess NH3. This dark blue or deep blue solution, very beautiful solution in excess NH3 for the copper 2 hydroxide, because there's an underlying reactions that I won't talk about here. This was in excess NaOH. The precipitate still around, they remain insoluble, that's why they're at the bottom. This is just the NaOH solution, which is mostly just water lying around. Okay, so there's the precipitate remaining insoluble in excess NaOH for the blue color, the pale blue color precipitate, which was the copper 2 hydroxide. This is actually not copper 2 hydroxide anymore. Something has happened, and I'll talk about it in another tutorial video, specifically on the case study of copper 2 chemistry as part of the A-level A2 transition metal topic. Okay. The last one I did was also A-level paper 3 cation. There's the manganese 2 or Mn2+, and it gives you that off-white precipitate. Looks like white at first, but I think within 5 seconds they already gone off to this color. So this color is not white precipitate, it's an off-white precipitate. Both of them, they were insoluble in excess of NaOH as well as in excess of NH3. Okay, so thank you for watching, and I hope the qualitative analysis here provided you further insights and at least give you the opportunities to differentiate and to distinguish the color, which you might not have realized when you actually did this practical in the lab. Which of course, if you get the opportunities, that's good on you, but if you haven't, because of the pandemic, you know that paper 3, when it happens, it will not be alternative to practical. It has to be you doing the actual practical, and that's what made me really interested in chemistry to begin with, is a lot of these colors and of course many other things as well. I always found chemistry easy, but it's not necessarily easy for a lot of people because of these little things. Alright, so what else do I need to say? Oh yeah, please subscribe to the channel, click the button on the bottom right, and yeah, please share the channel widely with all your friends, your chat group, your study groups, your juniors and your seniors, whether they're doing the O-level or the IGCSE 14 to 16 years old curriculum, or if they are doing the A-level like you do perhaps, or the IB curriculum, the 16 to 18 years old curriculum, then the A-level topical playlist will be more suitable for them. Alright, so follow me at ptet.chemistry, that is ptet.chemistry on IG, Facebook as well as Twitter if you use this social media platform, or if you plan to return to in the near future. I look forward to connecting with you and letting me know how it all goes for you, for the exams, with the results, and I don't know, 5 years, 10 years, 20 years from now, if you remain connected, you can perhaps tell me when your children actually uses these videos, and yeah, we never know. Okay, so thank you for watching again, and I'll see you in the next tutorial video. Alright.